So what we're going to look at now is we're going to look at drawing some graphs and utilizing something called the second derivative test, or at least look at the second derivative test and then actually put together what we've learned inside of this lesson in order to draw some graphs. So this thing is called the second derivative test, and so here's what it states. Suppose that f double prime is continuous near C. Okay, so again, we're talking about within an open interval around C. So it's got to be continuous in an open interval around a certain point C. If f prime of C equals 0, and f double prime of C is greater than 0. So if f prime of C, so if we know that C is a critical number, right, because f prime of C equals 0, and we know that f double prime of C is greater than 0, so what we're looking at is that it's concave up, then f of C is a local minimum. We'll take a look at that. Let's see that. So here's a local min. Okay, and so we're saying, let's say this here is C, and so I have this point here, and it's a critical number, all right? And then I also know that it's concave up. Now what you get here is that it's going to look like this, okay? It must be a local minimum, right? Okay, it can't possibly be a local maximum, right? In fact, it can't be anything other than a local minimum, if you think about it. And we also can't have it going the other way. It can't be concave down, because what we'd end up with is we'd end up with a cusp, which is going to be not differentiable. So consequently, we have these two characteristics, we get a local min. Now, if f prime of C is equal to 0, again, we've got a critical number, and f double prime of C is less than 0, then f of C is a local max. So here we've got a local max, all right? And we want first, we've got a critical number, okay? And around that critical number, it's concave down now, okay? So we're down, concave down, right? So let's say, for example, this is C, and so we want to be concave down, so that means that our function's got to look like this. Okay? And that's the second derivative test. The second derivative test will tell us if we have a local minimum or we have a local maximum. Okay? All right. Now, let's go in and let's utilize maybe this and some other work in doing some graphing. So now let's consider the function h of x, which equals 5x cubed minus 3x to the fifth. We'll find the intervals on which f is increasing or decreasing. So what we want to do in order to determine increasing or decreasing, right, is derivatives, the first derivative, and we want to know positive or negative. All right, so first what we're going to do is we'll find h prime of x. And so h prime of x is going to be 15x squared minus 15x to the fourth. Then we're going to set that equal to 0. So that'll be 15x squared minus 15x to the fourth, and I'm just going to do some factoring. This will equal 15x squared times 1 minus x squared, which will be 15x squared times 1 minus x times 1 plus x, and we'll set that equal to 0. So looking at that, that's going to give me my critical numbers. X equals 0, x equals 1, and x equals negative 1. So those are my three critical values. Now what I'm going to do is I'm actually going to test those critical values, or the critical numbers, excuse me. So first, negative 1, 0, and 1. Okay, I'm going to put them out on a number line, and then I'm going to test the first derivative, so h prime of x. So h prime, and we'll choose first, let's use h prime of negative 2. And h prime of negative 2 is going to end up equaling negative 180. Okay, so that's clearly negative, so that's decreasing. H prime, now we'll choose negative 0.5, okay, and that's going to equal 2.8125, okay, and that's going to end up being positive, and so hence it's going to be, the function will be increasing on that interval. Now we'll do h of 0.5, and that'll also be 2.8125. So that'll also be positive and increasing on that interval. And then we'll have h of 2, and that'll equal, again, negative 180. So that'll be negative, and hence decreasing. So h of x is decreasing on negative infinity to negative 1, not including 1, union 1 to infinity. Okay, so that's where it's decreasing. Notice that I didn't include 1 because at 1, it's neither decreasing or increasing. Actually, we have a critical number. Then we have h of x is decreasing, is increasing on negative 1 to 0, union 0 to 1. And again, notice that I didn't include negative 1, and I didn't include 1 or 0 inside of this particular interval. And that's because those are critical numbers, and they're not actually places where the function is in fact increasing. So now let's look at where to find the local minimums and maximum values. In this case, we're not actually going to have to use the second derivative test because what we have is it's very clear where we have the local maxes and mins. So notice that on either side of negative 1, on the left-hand side of negative 1, it's negative, and on the right-hand side of negative 1, it's positive. So that means that we have a local minimum at f of negative 1, okay, which will equal negative 2. Then we'll have a local maximum at f of 1, right? And the reason why we know that is because it's increasing on the left-hand side and decreasing on the right-hand side, right? We went up and then down, okay? And so that ends up equaling 2, all right? And that's our local maximum. Now, let's find the intervals of concavity and the inflection points. So we'll want to find h double prime of x. And h double prime of x is going to end up equaling 30x minus 60x squared. 60x cubed, excuse me. Okay. Now, we want to set that equal to 0 in order to find our inflection points. So we got 30x times 1 minus 2x squared is going to equal 0. Okay. So we'll let x equal 0. And that'll be 1 minus 2x squared will also equal 0. Okay. So 1 minus 2x squared equals 0. That'll give me negative 2x squared is equal to negative 1. X squared is equal to 1/2. So x is equal to plus or minus the square root of 1/2, which is equal to plus or minus root 2 over 2. So those are inflection points. So our inflection points are going to be at x equal to 0, x equal to negative root 2 over 2, and x equal to root 2 over 2. Okay? Now we're going to go and test them, just like we did with the increasing and decreasing intervals. So here's negative root 2 over 2, here's 0, and here's root 2 over 2. Okay? So now we've got h double prime of negative 1 is going to end up equaling 30. So that means that on this interval, the second derivative is positive, and in addition to that, we have that it means it's concave up. Okay, h double prime now of negative 0.5 is going to equal negative 7.5. And so this is negative, and hence on this interval, we're concave down. Then h double prime of 0.5 is equal to 7.5, and that's now positive. And so on this interval, concave up. And then h double prime of 1 will end up equaling negative 30. And so on this interval, we are now negative, and the function is concave down. All right, so second derivative, set it equal to 0 to find our inflection points and then test on the intervals in between. All right, so let's actually synopsize this. This means the function, well, let's call it h of x, is concave up on negative infinity to negative root 2 over 2. Notice again, I'm not going to include root 2 over 2. Union 0 to root 2 over 2. And concave down on negative root 2 over 2 to 0, union root 2 over 2 to infinity. Okay? So now all this information, kind of put it over to the side so that we can use it, because now what we're going to do is we're going to do some graphing. So now let's graph the function. We use this side in order to do that. Okay? And so let's start out with our critical numbers. Right? We have a local min at h of negative 1 equal to negative 2. So that's going to be right here. Okay? We'll have a local max at h of 1, which will equal 2. H of 0 is going to equal 0. So we'll know we'll put it right there. Okay? We are going to have inflection points at x equals 0, x equals negative root 2 over 2, and x equals root 2 over 2. So those are a little past 1/2. Okay? We can go in, if you want, you can put them in. I'm just going to kind of roughly draw them, roughly sketch them in. So maybe right about here. Okay, and another one right about here. It's my inflection point. Okay. You can actually, you don't even have to like write down where it's increasing because it's kind of clear where it's going to increase, right? But we do know from the second derivative rule that we're going to be concave up, or excuse me, concave down around that local maximum. So it's going to look like that, okay? And we're going to be concave down, okay, around our local minimum, or excuse me, concave up around our local minimum. So it will look like that, right? So we've got concave up here, concave down here, okay? And then we switch concavity. So since we went from concave down on this interval, we're going to now go to concave up, right? And then at 0, we'll switch concavity. We'll go from concave up to concave back down. And that's a picture of our graph. Okay, I started out with the local mins and maxes. We'll see a little bit later that you're also going to want to use some intercepts in here. Plot in your inflection points, okay, and then draw the graph based upon where the graph is increasing and decreasing and where its concavity is. Okay, so we want to make sure that we also include increasing, decreasing intervals and concavity changes and concavity. So there it goes, right? Basically, first derivative test to determine whether or not the function will be increasing or decreasing. Okay. Find your local mins and maxes. Yes. Either utilizing the second derivative test or utilizing where the function is increasing and decreasing around our critical numbers. Then what we'll do is we will go in and find our concavity utilizing the second derivative. So set the second derivative equal to 0. And then now that'll help you to find your inflection points, right? Once you find your inflection points, then you utilize the intervals and maybe a number line in order to check your points, okay? Then put it all together, graph it on onto a graph, and that completes it all. So this completes the lesson.